All right, class, it's time for week 2. Hopefully, you're all having a good President's Day weekend. I'm recovering from a little cold, but I'm getting there and starting to read some of your homework assignments and your responses. So that's exciting. Look for your grades soon. But in the meantime, we're going to get started with week 2. So we're going to cover the hydrologic cycle this week. Don't worry about that math. We're not going to do that just yet. But the blue planet, right? That's us, Earth. Call us that for a reason. There's certainly a lot of water on this planet. And it doesn't stay put, right? It moves. And it changes when it's moving. So we do have vapor, we have liquid, we have ice, right? We have different types of water. And it's found in different places under different circumstances. So we're going to talk about that a bit tonight. But we're also going to talk about the way that humans interact with this cycle, how we've changed the cycle for better, for worse, and what that means for us now. So, changes of state, water movement, and water storage are the big themes today. Changes of matter, solid, liquid, and gas, right? We don't think about it in those terms usually when we're talking about water, right? Solid water is better known as ice. Liquid water is usually just called water. And gaseous water, sometimes, steam, something like that. But it is solid, liquid, gas, and that's an idea that is applicable to all matter. Um, we're just going to talk about water in specific today. So matter is composed of particles, and the type of particle determines the identity of the matter. The physical state that matter exhibits is based upon how the particles are arranged, okay? So you may have heard H2O, right? In all of those states, liquid, solid, and gas, it's still H2O, but it's how those H2O molecules are arranged that determines what state it's in. So here you can see kind of a little demonstration of that here. In ice, it's a solid, so it has a very rigid form. You can see there's a lot of like structural strength in the way that the molecules are positioned. Here in water, they're a little bit closer together, actually, right, which makes water very dense. Um, but they don't have that same structure. And then in gas or steam, they're very far apart, right? The molecules are sort of out there floating on their own. The physical state that matter exhibits is also based upon its energy level. So that's an interesting idea. There is energy stored in matter, in all matter, right? That's what happens like when we burn something, we burn coal or wood or what have you, we're releasing its energy in a sense, we're breaking it apart. Um, Same here. So when solid goes to liquid, there is an energy transfer, there's an energy release. And it takes, in some cases, energy to move one from one state to the next. That's a photo of dry ice. And dry ice, I don't know if that's dry. That might be regular ice. But it's undergoing something called sublimation, right? In this photo, you can see that the ice, the solid ice, has gone directly to a gas. You can see the vapor underneath the spoon. That's a process known as sublimation. What it's done is skipped the liquid state, right? It's gone straight from solid to gas. So, some ideas here. There's just 3 states, like I said, ice, water, and steam or water vapor. Here's what the cycle looks like if you want to follow it all the way around. So going from a solid to a liquid, right, around the side here, we've got the terms that have energy embedded in them. So when a solid melts, when the ice melts into liquid water, call that melting, and there is some energy transfer there. Liquid evaporates into gas, that's some energy transfer. And then, like I just showed you guys in that photo, if it goes all the way from solid to gas and skips over liquid, that's called sublimation. On this side, so that was where energy is being added, right? We're getting, in a sense, hotter as we go down. Now, when energy is being taken away, in a sense, it's getting colder, right? Gas going to liquid, it's known as condensation, and then liquid going to solid is freezing. And just like sublimation, when solid goes all the way to gas, gas can go all the way to solid. That's known as deposition. Not something that's very common, but it is possible. Right, sublimation, something like dry ice, that's one that folks always kind of have a hard time with. The physical change from liquid to gas is called evaporation. The energy to make this change occur comes from the sun. So this is something that we see in the natural world all the time. If you leave a glass of water out on a hot day, you're going to come back to find that over time it's evaporated. This happens off of natural bodies of water. This happens off of blades of grass, for example, right? If you water your grass in the heat of the summer, not all of that water is going to make it down into the soil. Some of it's going to sit on top of the blades and evaporate right off of them. So, building on that idea, there is something called evapotranspiration. Okay, so part of it is when water evaporates from the leaf's surface. That idea we were just talking about, where the water that's sitting on top of the blades of grass just evaporates right off because of the sun. But also, there is water that is put into the soil or exists in the soil, is sucked up by the plant, and it's absorbed by the roots. It goes up into the plant and is used and then evaporates off of the leaf surface. That's known as transpiration. Think of it, to me, I think of it like perspiration, right? Humans, we sweat. That's our built-in cooling mechanism, right? We sweat, the sweat is on the surface of our body, it then evaporates, and that evaporation is essentially a transfer of energy that cools us. So, same with the plants, they use it as a cooling mechanism as well, and just part of their natural state. So, that is transpiration, right? We look at that process, a biological process, and then we look at just the evaporation that is naturally occurring on top of the plants anyway, and we call that evapotranspiration. So this is the amount of water that evaporates. It's a physical and a biological process. Okay, the evaporation is physical, the transpiration is biological. Then you should have a general concept of what the melting point or the freezing point is of water and the boiling point. Very easy in Celsius, right? The freezing point is 0. In Fahrenheit, hopefully you guys might know, 32 degrees. And the boiling point, same idea, very easy in Celsius. It's 100. And this is for water, right? That I'm giving you these figures, but they are different for each substance. Volatile substances are really eager to change states, so they have low boiling points. So again, melting point for water, 32 degrees Fahrenheit or 0 Celsius, and 212 degrees Fahrenheit or 100 Celsius. And there is something known as a triple critical point. Um, this is one of those things, I'll be perfectly honest, I have never used it in my real life, in work or anything like that. But I have heard that it may be on the water use efficiency exam. So just something to tuck away as a little bit of knowledge. The triple critical point for water is the same as the melting point. So it's 32 degrees Fahrenheit or 0 Celsius. Okay, so now there's a few Q&As. Okay. What are the three states of matter? Solid, liquid, and gas. Not too hard, right? I guess that would be better if the answers didn't show up right away. Okay, what is the term for the transition from the gaseous state to the liquid state? Gas to liquid. Condensation, right? You think about that condensation on the outside of your glass. So when you have a nice cool beverage, the air that is touching the sides of that glass is cooled because the contents of the glass are cooler than the surrounding air. And that causes the water vapor that's held in that air to become liquid, to condensate, and sit on the edge of your glass, right? That's what's happening there. What is the term for the transition from the solid state to the liquid state? Melting. We think about it, without really thinking about it. Ice melts, but it is, in fact, the transition from the solid state to the liquid state. Okay, normal boiling point for water, definitely easier to remember in Celsius, but 212 Fahrenheit as well. And the triple critical point, which is also the freezing point / melting point. There you go. And what is the term for a substance that will readily change state from liquid to gas? Volatile, right? These are things like chlorine, right? Chlorine is volatile when it's in its liquid state. It wants to expand and become a gas rapidly. If any of you work in and around a treatment plant, you might be familiar with that concept. And what is the term for the combination of processes that change liquid water into the gaseous state? This, I cannot emphasize this one enough. Evapotranspiration. You'll often see it as the combination of processes or the combined physical and biological processes. The idea here is it is two processes, evaporation and transpiration, kind of balled up into one, and it's water evaporating through the plant itself and then off of the plant's leaves. So evapotranspiration. All right, a little bit about water movement. That's a really pretty way for water to move. But there's other ways as well. So a force is necessary to move any matter. The force of gravity causes water to move downhill. That's that beautiful waterfall we just saw. But there is a way to get water to move uphill, but energy is required. In nature, the energy that we use to move, or that nature uses to move water, is the sun. It's something that we don't think about often, but that evaporation, right? That's water being lifted off of the Earth's surface into the Earth's atmosphere because of the temperature and because of solar radiation, right, coming from the sun. So what do we do in a water system where, let's say, we want to move a water uphill? Well, we can't rely on the sun to do that for us. It will move water uphill eventually, but it'll move it so far uphill, it'll be in the atmosphere. So, how about a pump, right? That's a more controlled way for us to move water, and we use electrical energy to power our pumps. There's another very dramatic way for water to move, but that's not the only way. So that is actually like thermal expansion, right? The water has been heated geothermically underground and is forced up through a small opening, causing that dramatic geyser. Okay, so this is just a really simple way to look at how water moves. At here in the left-hand corner, you see precipitation. And it's kind of easy to start there, right? That's where we think of water maybe as entering the cycle. So it falls down to earth from the clouds, and some of it percolates down into the ground. Hopefully, that's the goal. And then a lot of it in our urban area, the majority of it, becomes runoff, right? And then it goes into a body of water, be it a lake, stream, river, ocean. And then eventually, that surface water is exposed to enough sunlight and enough heat that it evaporates. Or here we even have evapotranspiration. So some of that runoff and some of this percolation could also encounter, say, plants and be used by those plants and become evapotranspiration, right? And in any case, it ends up back in the atmosphere and eventually back down as precipitation. Precipitation, by the way, I mean, I keep calling it rain, and that's because I'm a Southern Californian. But it doesn't have to be rain, right? It can also be snow, hail, I don't know, sleet perhaps. Not too familiar with all the forms of crazy weather. But it's any circumstance where water is coming out of the atmosphere in a liquid form or even solid form in the case of snow, and hitting the Earth's surface. So, water movement in the hydrologic cycle, surface to atmosphere, right? So now we're thinking about moving up from the surface up into the atmosphere. That's evapotranspiration, right? The combined term, be it from plant or from evaporation. And then atmosphere to surface, that's precipitation. Surface to subsurface, percolation, right? So that's that guy right here where it's sitting on top of the surface and then making its way down through the ground into hopefully the water table. That's percolation. And then surface to surface, right here. So now it's already hit the ground. It hasn't percolated. It hasn't become groundwater. It's still running along the surface, maybe into another body of water or eventually onto plants, what have you. That runoff is, well, surface to surface flow. Percolation can also be subsurface to subsurface. So that means that percolation, this arrow is a little bit deceiving that it shows it just going straight down. That's definitely not how groundwater travels in real life. A lot of times it's going side to side, and it can take quite a circuitous route before it ends up going down. So that's what that little note there, percolation, is also subsurface to subsurface. And percolation has a few names, and we tend to use them all a little bit interchangeably. If you've ever worked with groundwater management, They're really fond of the term recharge, right? Because we think of our groundwater basins as a source of water for us. So we think about that water infiltrating the basin as recharging it for us to use. But, percolation, that's maybe more of a term from geology, but it is a term for when it actually passes through the soils and the soil profile. And then infiltration as well is another perfectly acceptable term. So you should be familiar with all three. They are used interchangeably. Okay, here's a little bit of an idea of how this all factors in for us. Told you we'd do a little bit of storage. So we do have surface soil up here, and this soil can be infiltrated, right? Water could flow through it and enter this unconfined aquifer. Here you'll see something called an aquitard. So an aquitard is a layer of dense soil, often clay-like, something like that, that slows, it retards the flow of water. It's an aquitard. It slows that water down. Then in the confining bed down here, you see an aquiclude. That is water's not going any further. Nothing gets past the aquiclude, okay? And then eventually there's some other layers down here. This is fairly typical for a groundwater basin. There's different geologic formations down there, and that's why not all groundwater basins are, or I should say, not all basins are fit to hold groundwater. Sometimes these aquicludes make it so that the groundwater is so low it's impossible to drill to, or sometimes the water up here is somewhat like in this example, it's held so closely to the surface that a lot of pollution comes through the surface as well. So it's not suitable for drinking in that sense, or it's very subject to pollution. So there is a little bit of science in figuring out which groundwater basin is the best, or I guess you sort of get what you get. You don't really get to change it very well. They do try to engineer some of the basins that they use for rainwater recharge. That's a pretty interesting science. But not all basins are great at holding groundwater, is what I'm trying to get at here. And there are different circumstances that can be caused. Like here, you see an artesian spring. That's because the water in this layer is held between two aquicludes, and this is indicating that it's under pressure, and that if you were to drill all the way down to that layer, the pressure down here is greater than the pressure at the surface, and that water would naturally flow. So that's known as an artesian well. All right. So that's it for the new material. We'll go through the Q's and A's here. What are the terms for the four main movements of water in the hydrologic cycle? Evaporation, right? Evaporation and transpiration added together to form evapotranspiration. Then precipitation. Remember, that could be rain, snow, something like that. Anytime that water is moving from the atmosphere onto the surface. And then percolation, right? That's water moving through the soil. And runoff, that's surface flow. Name two terms that can be used instead of percolation. So, like I said, please know these three terms. Please know that they're, for our purposes, interchangeable. What causes water to move uphill in the hydrologic cycle? Another way to think about that is what adds energy to the hydrologic cycle. So that is the sun. All right, so that is the first half of this week's material. Hope you learned something, maybe got a little refresher from something you already knew. But in either case, make sure that you know all this material. It's going to come up again in the quiz this week and in the future. All right.